Hello, welcome back to Compressible Flow. I'm Professor Steve Miller. Today, we're going to be changing subjects into an all-new module. This module, of course, is called Oblique Shock Waves. We are leaving behind our difficult restriction of having the flow normal to the wavefront, the normal shock wave. Oblique shock waves handle, of course, both normal shock wave, if certain assumptions are made, and the more general case of having the flow being not normal to the wave front, which we call the oblique shock wave. In this particular class, we'll introduce oblique shock wave examples. We'll look at Schlieren images and CFD simulations of these beautiful flows. Then we'll look at the so-called Mach angle, which we discussed earlier, and rederive it. We'll look at the relation of the Mach angle to the oblique shock wave angle, which is the angle of the flow relative to the shock wave. Once we look at these properties and images, we'll then introduce the so-called oblique shock wave theory, which are the equations to describe and predict the flow across oblique shock wave. And we'll use our previously developed approaches to do this. And you can see why we have logically laid out the class in this manner. We'll then look at the famous oblique shock wave diagrams to help you understand the physics. And we'll find the so-called and all famous theta-beta Mach number equation and look at its solutions on the theta-beta Mach number diagrams, which are included, of course, in your class handouts. Let's get started in this beautiful theory, which I'm sure you'll enjoy. Now, normal shock waves are a special case of oblique shock wave. If we let our oblique shock wave theory have a flow angle of 90 degrees relative to the shock wave front, we will indeed find that we recover all the normal shock wave equations which we found earlier. So the normal shock wave case is a limiting or assumed case for a specific angle of oblique shock waves. It makes sense because our oblique shock wave should indeed be compatible with our normal shock wave theory. This is a goal of our analysis, and it makes physical sense to search for this goal. We'll also say that oblique shock waves, and this is an informal way to think about it, occur when the flow is turned into itself. The opposite phenomena happens when the flow is so-called turned out of itself. This is just like the analog of the piston shock tube problem. When the flow is compressed, the piston moves and a shock wave forms through coalescence of waves. If a piston moves in the direction of the shaft of the piston, then of course an expansion wave forms. This is just like a flow turning into itself and out of itself by some solid structure in a supersonic flow regime. Take a few seconds and consider these statements. Now, these oblique shock waves will contain many of the same properties as normal shock waves because, of course, it's from the same set of physical equations, the Navier-Stokes equations, and it's the same theory. However, you see the turning angle of the flow, which we'll define formally soon, will dictate these properties, and some will be broken and some will remain the same as the normal shock wave thermodynamic properties across the shock wave itself. Let's get started looking at these particular problems, and I think you'll enjoy this very much. Take a few seconds and look at this beautiful picture of figure 237 of my slide deck. It says, and I write, a Schlieren of an oblique shock wave attached to a corner flow. Take a few seconds and think about what you're seeing. First, the flow moves from left to right. The solid black part of the figure represents a solid structure. It's represented at the wall as a plane surface, which instantaneously changes around this location at an angle, maybe 5 degrees, right here. So you can see here's the wall at maybe 5 degrees, and here's the wall at 0 degrees. Up here, this is all about the same color, so I'll say that's just the ambient supersonic flow. And just like in normal shock waves, you must always have a supersonic flow in front of a shock. The supersonic flow in a shock is right here. This dark black and white line represents the density gradients of the Schlieren image, where the oblique shock wave is. Behind the shock, you have some disturbances. Along the wall, you see there's also some kind of disturbance in the Schlieren. And it grows and actually comes off the wall, located where the shock is, and goes along the wall and becomes thicker and thicker. There's undoubtedly a turbulent boundary layer which has become much thicker and larger after the location where the oblique shock wave is attached to the wall. So anywhere you have supersonic flow, say around an aircraft or a space vehicle going in the atmosphere, you indeed have oblique shock waves forming wherever there's flow turning angles, that is, where the surface changes angle on the wall or skin of the vehicle. Let's look at this in particular examples and diagrams. Here's a more complicated case. In figure 237, we looked at a single oblique shock wave. In this figure, it's a famous figure. We see, in my caption I wrote, the NASA X-15 wind tunnel test. It's very much interesting to look at the history of the X-15 program. The X-15 was an experimental aircraft developed by NASA, which was, of course, flown by the Air Force, and it had many famous test pilots, which became, of course, astronauts who landed on the moon. Nonetheless, in the picture, it's also a Schlieren. Here's the sting of the wind tunnel to measure the force balances, and here's the aircraft itself. This is the outline of the X-15 aircraft, which I shown earlier in this very class in previous modules as an example. Out here, the flow is undisturbed and it's supersonic. So the flow out here in front of the aircraft, in front of the shock waves, knows nothing about the aircraft. Now you can see along the aircraft itself, and it's a three-dimensional body, and this is a three-dimensional projection onto a two-dimensional surface, which is the Schlieren. You will see shock waves coming off the aircraft. Now these shock waves are not two-dimensional, treated two-dimensionally like a plane surface like in figure 237. They're actually conic. And so the shock wave coming off the leading edge of this X-15 model is actually like a cone, and the tip of the cone is located at the leading edge roughly of the aircraft itself. We're only seeing the two-dimensional projection of it. You can also see shock waves coming off the aircraft at different points. Indeed, shock waves are coming across the whole region. And so you can imagine that after the shocks, indeed, the flow can be supersonic or subsonic, but we do know that in front of every one of these shock waves, which represents these lines coming off the Schlieren image, that we indeed have supersonic flow locally in front of all the shocks. You can also see there's some darker colors here and lighter colors on the opposite sides of the sting, which represents the growing turbulent wake and boundary layer. And so you see in the model test vehicle or out in the atmosphere where shock waves occur on vehicles, there's a scaling which matches one-to-one from the wind tunnel test in terms of angles and Mach numbers in front of the shocks, as long as you're matching the Mach number in the wind tunnel and flight test. Here's another example which we have not considered in the class. This is a picture of, in the top, of the beautiful SR-71 aircraft in flight and takeoff. You'll see in the engine exhaust, there's a number of, informally, we call shock diamonds because they look like diamonds, but formally, the shock cell structure. We see cells. Each one of these little diamond areas we call a particular cell. And they're not always diamonds, so don't call them shock diamonds. Call them shock cells and shock cell structure collectively. You'll see that each one consists of a system of shock waves and expansion waves, which are semi-periodic. So this is the full-scale vehicle flight. We can also take one of our nozzles, which we talked about previously, a converging diverging nozzle of the particular aircraft or rocket engine, and put it in, of course, a small-scale facility. Here's a little model where we have a high-pressure, high-temperature air exhausting from a nozzle through a converging diverging stream tube, which represents the nozzle. You'll see in this case, we also get the beautiful shock cell structure. If the operating conditions, the nozzle pressure ratio and temperature ratio, closely match the engine and the 1-inch nozzle diameter test case, we'll find the exact same shock cell structure between flight test and experiment. In this beautiful case, you'll find indeed that the distances and shock wave angles and their properties are exactly the same, but scaled between the flight test and experiment. So indeed, we don't only see shock waves appearing on the outside of our vehicles attached to their airframe, we also see them in the exhaust from the engines. And we also see these types of shock waves appearing inside the engines and the inlets, as we talked about at the end of our previous class on normal shock waves. Let's look at, say, a particular computational fluid dynamics simulation where I'm showing here in figure 240 of the slide deck instantaneous and time average CFD solutions of the oblique shock waves in a particular corner. So this corresponds to the Schlieren, which I showed in 237 of the slide deck, but now we're looking at, of course, figure 240 of the slide deck. In the lower figure is very much what we would see in the Schlieren with a long exposure time of the camera. Here the flow moves from left to right, and it's a time averaged flow field, which I'll talk about momentarily. This blue area is all supersonic, and this line here represents the shock wave, and the multiple colors along the wall represent the boundary layer. So the flow goes in at, say, 0 angle of attack, and it hits a corner, and it's instantaneously turned by the corner at some small angle in degrees. This is what's forming the oblique shock wave, a small turning angle of the flow, where the flow is so-called turned into itself at supersonic speeds. Indeed, here the flow is likely supersonic behind the oblique shock wave. And so we have supersonic flow everywhere in the flow field, behind the shock wave included, except for the turbulent boundary layer, because we have a no-slip wall condition. Let's now look at the upper figure. This is the so-called instantaneous flow field. Now the bottom flow field takes every fluctuating value at every point in space and time averages it over the exposure time of the camera. In CFD, we're able to calculate the instantaneous flow field everywhere in the flow domain, which is a major advantage of CFD, which we do not have in experimental work or theoretical work unless we have an analytical solution. Here, once again, we have the undisturbed median. It's exactly like the time average. There's no fluctuations. We still have that shock wave, which appears relatively at the same location as the time average version. But you see now, the boundary layer is not nice and smooth. In fact, it has large turbulent eddies, which are kicked up by the shock wave being attached to this turning part of where the shock wave attaches to the turning angle of the solid wall. Take a few seconds and think about the instantaneous real-world physics compared to the time average value. Remember, in our class, we're assuming that we have statistically stationary solutions. And therefore, we are time averaging the flow quantity, so to speak, of turbulence. This is what it means to have stationary or statistically stationary solutions. We're looking at a stationary type of flow field. The actual flow field in vehicles and in the real world always has, in practical situations, turbulence. And the turbulence is unsteady and chaotic, and it looks more like the upper picture than the lower one. Nonetheless, let's analyze the stationary problem. So looking at this previous picture in the bottom figure and figure 241, I've drawn the wall, its turning angle, and the position of the oblique shock. Just like before, we'll have a supersonic flow coming in from left to right, and it goes through a shock wave, and we go to from state 1, the supersonic flow, to state 2. The wall is drawn here, and the shock wave attaches to the turning angle of the wall. This is because, of course, we need to enforce continuity. If we don't do this, then of course the flow would be going through the wall, which would be a devastating problem. You'll see that this actually breaks down and the shock wave can detach from the corner and form, of course, a strong shock solution, which we'll show later in these classes. So the shock wave is drawn as this line, and the wall is drawn with a line with ticks. The flow turns at an angle theta. We call that angle theta the flow turning angle. There's also going to be an angle from the dashed line, which is the initial flow direction along the wall, parallel to the wall, and it's turned, of course, by an angle theta, that's the flow turn angle, but the shock wave angle we call beta. The angle beta will be from the shock wave to the dashed line, the initial flow direction. Now, thermodynamic properties are the same as the stationary normal shock properties. The density will go up over the shock, the temperature will go up over the shock, and the pressure will go up over the shock for every shock. And remember, these values are indeed static properties. We have not talked about what happens to total properties yet. We also observe experimentally that the Mach number, M2, is always less than 1 across any particular shock. This holds for all shocks. And so we observe Mach number going down and thermodynamic properties going up. Let's make some notes on our observations from the Schlieren, the CFD, and our diagram, and initial physical observations of oblique shock waves. First, we noted that in reality, all oblique shock waves are truly three-dimensional and always in supersonic flow locally in between the wavefront. This is true, of course, even in planar experiments, like a planar ramp or turning angle, and also in three-dimensional, say, flows over nose cones. The images we view are always projections of the three-dimensional flow field into a two-dimensional plane, which is, of course, like the surface of our screen. So the development of our theory will be based on a flow bounded by one particular side, that is the wall. And from our diagrams, we've seen that in every case, there's a flow deflected or turned into itself by a particular angle, theta. You can see here the flow is turned by theta, and the streamlines are instantaneously turned. It's an oblique shock wave because the angle of the incoming flow is at an oblique angle relative to the wavefront, as you see in the incoming streamlines, and 1 relative to the wavefront. You'll also know that the streamlines instantaneously change direction, which is a property of supersonic flow, of course, and they remain relatively parallel to the wall, which is an angle theta. So you can see that the flow has turned into itself by an angle theta. Now, unlike normal shock waves, stationary oblique shock waves are functions of x and y, while normal shock waves are only a function of x, which are standing. Now, indeed, the source of these types of shock waves is exactly the same as normal shock waves. You could view their formation in two ways. One, it could be that a coalescence of disturbances occur which coalesce into a shock. It is much more realistic and physical to view the formation of a shock wave as a pressure mismatch in the domain and the flow turning and creating the shock wave so that the pressure mismatch can be formed. Otherwise, there's no other way for the flow to move without the discontinuity. You'll see this in the equations of motion. You might also remember the moving point wave or point source example we done way back in the beginning of the class. Here's our recollection of these figures. On the left, we have a subsonic moving point source moving from A to B, and there's a collection of circular disturbances as it moves from A to B in the concentric circles. If the disturbance moves at a velocity greater than the speed of sound, which we call a in this particular figure, then once again, we have a Mach angle mu. Remember the Mach angle discussion. The Mach angle or Mach waves are formed by a coalescence of acoustic waves in the flow. And so you see, it is not possible really for the coalescence of acoustic waves in this particular flow to coalesce at the shock position. What happens, of course, in the normal shock case? Are we able to have our waves coalesce at the normal shock location for external supersonic flow? Think about this problem for yourself. Let's review our formulation for the Mach wave. Remember, in a supersonic flow, in the case shown previously, there's a wave which is formed, and the Mach angle, that is the angle mu in the right-hand side of figure 242 of the slide deck, will go as sine of mu of ct over ut, which will go as c over u because time cancels, which will go as 1 over m. And therefore, the Mach angle goes as sine negative 1 of 1 over m. So you can see, indeed, that this case can be derived analytically. Now, the coalescence of these Mach waves create a very, very, very weak disturbance. And if the disturbance is strong, a wedge might create a very strong so-called Mach wave or oblique shock wave. If the disturbance is weak like the acoustic pulse, it creates, of course, a very, 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 very weak shock wave called Mach wave. It's not really a shock wave at all. This coalescence occurs at an angle beta. That shouldn't be angel, it should be angle, excuse me, into the free stream flow. Here's one more picture. Here we have a shadow graph with a zebra stripe background, and I showed this image in the beginning of the class. The zebra stripes just are vertical lines. You can see where the oblique shock wave forms here that indeed the lines are disturbed because the density gradient occurs across the shock and the light from the light source is bent by the shock wave surface. You can also see bending of the zebra stripes by the density gradients within the supersonic flow of the turbulent boundary layer around the cone. Now we'll note that the Mach wave angle is much smaller than the shock wave angle. So look at our calculation of mu. Mu in this case is the Mach angle. The incoming flow is supersonic and it moves over a cone, and the half angle we would call theta, which is the original flow direction through the center axis of the cone to the flow turning angle. So theta is the half angle of this wedge case. The oblique shock wave is here as the very dark line. A Mach wave will appear along the dashed line. The shock wave angle beta is always greater than the Mach wave angle mu for these particular cases, no matter what. So beta is always greater than mu. You can always use this to check your solutions and check if beta is greater than mu as being physically true. So we observe these phenomena from experiments and of course CFD. But we have not found out what is beta and what are the properties across the shock. We still need to seek these properties. So let's analyze this problem with a particular control volume. Remember, a Mach wave is a limiting or weak shock case of the so-called oblique shock wave. Now let's focus on the oblique shock wave diagram and put a control volume exactly across the oblique shock where my cursor is moving, or here. So we'll call our angle of the shock wave relative to the incoming flow direction beta. The angle which the flow turns, that is a streamline, could be plotted as an angle theta. Here's theta. Now, we'll have some incoming velocity, say v with m1, and an outgoing velocity across the wave, which is instantaneous turned at angle theta v2 and m2. These, of course, are two flow velocity vectors. We can decompose these as a velocity component which is tangential to the wave and in front of the wave. We'll call that W1 and M11, and a flow which is perpendicular to the wavefront, which we'll call U1 and MN1. The N stands for normal. The components after the shock wave will decompose in a tangential and normal component of W2, MT2, that's the tangential velocity, and the tangential Mach number after the shock wave, and the normal velocity, normal Mach wave, U2 and MN2 after the shock wave. Now, if we draw two of these streamlines along the oblique shock, we might show this between this upper figure on the same shock. We have a lower streamline, which might be represented here, and an upper streamline, which is also represented here. You'll notice in this particular fluid parcel is deformed by, of course, the turning angle of the flow theta. In this case, we still have V1 and V2, but now if we do a control volume formulation, we might view that there's certain faces of the control volume, A, B, C, D, E, and F respectively. A is an inlet, D is an outlet of our control volume, and B, C, F, and E, of course, have no flux across the surfaces because the flow vectors are perpendicular to the surface faces. So we would not expect to have mass, momentum, or energy flux on B, C, F, or E. Let's try and write down the mathematics for this particular problem, but let me write and mention the notation first, which I show on 697 of the slide deck. Now, here we'll write U1 or M1 is the velocity and Mach number upstream of the shock. U2 and M2 are the so-called velocity and Mach number behind the shock. Beta is the angle of the shock wave relative to the incoming flow direction, U1, and theta is the angle between the vectors U1 and U2, the flow deflection angle theta. That is also, of course, the angle of the vehicle. It's the angle which the flow turns through the shock wave. Remember, the shock wave can also be curved, as you saw in bow shocks, which are also oblique shock waves. So theta is actually a function of the position on the three-dimensional surface, which wraps around a particular vehicle in space and time. We'll also introduce MNI and MTI, which correspond to the normal and tangential Mach numbers respectively. Here I is 1 or 2 for the Mach number in front of and behind the vehicle respectively. Finally, as I showed in the previous diagram, V and W are the velocities normal and tangential to the shock front respectively, and I equals 1 for in front of the shock and I equals 2 for the float after the shock. Let's check this out now in terms of an application of a control volume. We will need to enforce conservation of mass, momentum, and energy, and perhaps an ideal gas law to solve and close the problem to cross from known properties in front of the shock to properties after the shock. Generally, in supersonic problems, we march downstream. So we know the properties in front of the vehicle, and we march downstream through the flow, that is in the downstream direction, the direction of the flow, and cross all these shock waves and expansion waves. Therefore, we must apply control volume theory to analyze each particular shock in regions before and after this flow. So 494, I apply, indeed, the control volume formulation. Now, we can write rho 1 V1 equals rho 2 V2, and look at that in the particular diagram on 678. Can you see why rho 1 U1 equals rho 2 V2? Also, U dot ds is 0 across the fluxes of the surfaces B, C, F, and E. Velocities does not cross those particular dotted lines in the cross-stream direction relative to the wave. And therefore, according to continuity, we can write rho 1 V1 equals rho 2 V2. Remember, V is not the magnitude of the velocity. Indeed, it is the normal velocities across the control volume surface in the way we wrote it in the particular problem, across the shock. Now, we can assume that there's no body forces. We'll say that gravitational effects are minimal in the region of the differential element across the control volume. And notice I placed underlines to denote vectors. Next, let's look at the tangential component of the momentum in the integral form. And so we're only looking at momentum equation in the tangential direction and, of course, the normal direction. Remember, the momentum equation is a vector equation, and so we have to look at all components. The third component of the momentum equation for planar oblique shocks, not conic oblique shocks, we're doing the planar problem, is into the page, so to speak, or the spanwise direction. And there's no flux whatsoever in that direction, so we'll just not worry about that equation. So let's look at the momentum of flux in, of course, integral form and reduce it through, of course, constant areas in the tangential direction for the momentum integral form. I've done the hard work for you in 496, and I have negative rho 1 V1 W1 plus rho 2 V2 W2 equals 0. The time derivative term is 0, the body forces are 0, and we're left with, of course, simply the momentum flux terms in the Reynolds transport theory. So look at our notation here relative to the wave fronts in the lower left part of figure 245 for W and V, of course. Now, we can divide that equation by the continuity equation, which we developed as rho 1 V1 equals rho 2 V2, and you'll have W1 equals W2. Indeed, we have shown through the continuity and tangential component of momentum equation that the tangential component and the velocities are indeed preserved across an oblique shock wave. And this holds true for all oblique shock waves which are planar. We have not examined the normal component of the momentum equation, which is what we will do now. We'll see this particular form written out in 498. So if I look at only the normal momentum fluxes, cancel out the time derivative term and the body force term, we'll find holding pressure gradients, of course, because there's a pressure gradient across the shock P1 and P2, the following equation 498. The momentum fluxes will be balanced by the change of pressure across the shock. And therefore I can write negative rho 1 V1 V1 plus rho 2 V2 V2 equals negative of negative P1 plus P2. That's straight up, of course, Reynolds transport theory written in a differential element across the control volume across the planar oblique shock. Try it yourself. We can rearrange 498 into 499, and we'll find the more traditional form of P1 plus rho 1 V1 squared equals P2 plus rho 2 V2 squared. Let's hold this equation and look only at the normal components in terms of the integral form of the energy equation applied to the control volume. Here, of course, we'll have energy fluxes across the shock and the pressure velocity term across the shock, which I write on the left-hand side. We'll have negative P1V1 plus P2V2 goes as negative rho 1, E1 plus U1 squared over 2 V1, plus rho 2 of E2 plus U2 squared over 2 V2 times V2. Work out this mathematics yourself and see if you can recover this equation. This is an exercise in the class, which I encourage. You can see that we can replace E once again by an enthalpy term. If we do this in 500 and rearrange our equations and simplify, we can have H1 plus U1 squared over 2 times rho 1 V1 equals H2 plus U2 squared over 2 times rho 2 V2. You can see here, once again, I've made an assumption. And the assumption, of course, is that we have a calorically perfect gas using perfect gas law. Now, we have put this equation in 501 for an obvious reason. We have rho 1 V1 equals rho 2 V2 in the particular equation. This means indeed that we can divide through by the continuity equation directly, and we'll have H1 plus U1 squared equals H2 plus U2 squared over 2. Therefore, and recall that U squared equals V squared W squared, meaning the magnitude of the velocity can be divided into its velocity components, V and W. Here, then, we can write and expand out U1 squared minus U2 squared equals V1 squared plus W1 squared minus V2 squared plus W2 squared. Why did I do this? So I can rearrange and also know from 502 a form of U1 squared minus U2 squared by subtracting U1 squared over 2 from both sides in 502. Also recall from the momentum equation, tangential form, W1 equals W2, as we just derived in equation 497 of the slide deck. Using these two forms and substituting, I can now find the particular reduction of the energy equation, which is H1 plus V1 squared over 2 equals H2 plus V2 over squared, which of course is our energy equation applied over a planar oblique shock differential element. Let's make some notes on what we found here. You'll see that these particular equations for continuity, two momentum equations, and of course an energy equation are almost identical exactly to the standing normal shock wave equations. And we've already developed a solution approach for those particular equations. We'll follow that particular solution approach almost exactly. In fact, the particular velocity components, which we found, the normal velocity components, are exactly normal to the oblique shock wave. And this is why we made this decomposition. And so we would recover a normal shock wave theory and its solution approach, which can be applied directly to the oblique shock wave problem. You see, this was a little bit smart on our parts to save us some work. Now, the property changes across the wave will be dependent on the normal components of the free stream velocities, just like the properties across a standing normal shock wave are dependent on the properties normal to the wave or in front of the wave. Therefore, we can use the exact same mathematical procedure for the normal shock wave problem, which we developed previously, to solve this set of nonlinear algebraic equations for the planar oblique shock wave problem. I haven't shown this work, but you're welcome to do it. All you would have to do is substitute in your oblique shock wave variables for your normal shock wave equations and follow the exact same approach. Or you can take the solutions themselves and make the substitution. And you'll find the following set of equations, which I summarized on slide 685. Here we are, and we find one particular equation, which is important, of 504. Remember, the properties across the oblique shock wave are dependent on the normal component properties, which are dependent on the wave angle beta. Because of course, beta dictates the wave angle relative to the incoming flow, as you recall in our decomposition of the velocity components. We can write mn1 equals m1 times sine beta. mn1 is the normal Mach number component of the vector Mach number in front of the wave to the oblique shock wave wavefront in front of the shock. m1 is the incoming Mach number in front of the shock. That's, of course, the magnitude of the vector Mach number in front of the shock, times the sine of beta. This equation is only found from trigonometry, shown here on the left lower part of figure 245. You can see we have mn1 and m1. The wave angle beta here is the angle between Mn1 and M1, of course. So you don't have to do anything except trigonometry to find that angle. Simple. Now the other equations are found like I just described. For calorie perfect gas, which we assumed, and I showed you where we assumed it in the solution process for developing the equations, we can find the following properties with substitution for M1 into Mn1. For thermodynamic values, in 505 we'll have a density increase of rho 2 over rho 1, ratio of densities across the shock, static values, goes as gamma plus 1 times Mn1 squared all over gamma minus 1 times Mn1 squared plus 2. In 506, we have the static pressure rises across the shock. These are 1 plus 2 gamma over gamma plus 1 times Mn1 squared minus 1. You can also then easily find, using ideal gas law, the ratios of temperatures across the shock by writing the ratio of pressures across the shock times the inverse quantities of density across the shock. T2 over T1 is P2 over P1 times rho 1 over rho 2, which I wrote in equation 508. So of course you can also find P2 and rho 2 and just directly use the ideal gas law to find T2. Or you could use ratios like in 508, or if you want to write it as a function of Mn1, you can substitute, of course, 505 and 506 into 508 and find out equation for Mn1 with gamma, which will give you only T2 over T1. Finally, the Mach number decrease across the shock is written as 507, just like we did for standing normal shocks, but with, of course, subscripts Mn1 and Mn2, respectively, for the right and left-hand sides. So we can have Mn2 squared equals Mn1 squared plus 2 over gamma minus 1, all over 2 gamma minus 1 times M1 squared minus 1. You can see this is a beautiful equation because it corresponds to the normal shock wave theory that's standing, but it's dependent on the normal properties of the Mach number. Mn2 is the Mach number after the shock wave vector component of M2, which is normal to the shock by angle beta. So in fact, you can find M2 and M1 simply through 504. Once you find M2, how would you find M2? Which of course can be done with another trigonomic operation, which you can find analytically through trigonometry through the diagram I showed just now on the previous pages. So we can show that M2 is found through geometry. So if we know Mn2 from, say, 507, we can then find through the sign of the differences of the wave angle with turning angle of the flow, M2. So let's make the following notes about our equations and their derivations. Remember, normal shock waves are only a function of one variable, M1. Oblique shock waves are only a function of two variables, M1 and beta. Now, M2 will be dependent on theta. Will this always be the case? Maybe or maybe not, depending on the relative velocities of the shock wave and position of the vehicle on the coordinate system. You'll also see for certain values of M2, the equations break down, even if we make calorie perfect gas assumption. And we'll illustrate this indeed in this class. So we need to develop further relations to look for additional properties. Let's do this soon. We have not discussed the relation of theta and beta. For example, what if we know Mach number and theta? Or what if we know theta and beta and not Mach number? Or what if we know Mach number and beta but not theta? We need to find the third important value which closes this system and solution approach. Now from our geometry only, we can see two tangential functions. The first is tangent of beta, the tangent of the wave angle, will go as V1 over W1. And you can show this and look and prove this to yourself through the trigonomic and outline which we showed previously. You can also show that tangent of the differences of the angles, beta minus theta, is V2 over W2. From our earlier momentum equation, tangential momentum equation, we showed that W1 equals W2. So we can combine 510, 511, and W1 equals W2 to find the following equation of 512. We can see tangent of beta minus theta, the tangent of the differences of the wave angle and turning angle, divided by tangent of beta, goes as indeed V2 over V1. You'll see W1 equals W2, they're replaced, and of course they cancel, and we're left with V2 over V1 on the right-hand side, with the left-hand side of 511 in the numerator on the top of 512, and the left-hand side of 510 in the denominator of 512. Try it out for yourself. It's super simple. Now let's combine this particular equation, 512, with the integral relations for continuity, momentum, and energy, which we've shown their results on the previous pages. You'll then find 513 in a simplified form of tangent of beta minus theta over tangent beta will go as 2 plus gamma minus 1 m1 squared sine squared beta all over gamma plus 1 m1 squared sine squared beta. Indeed, you will find this particular solution. And it's a workhorse equation. Now, we can simplify this equation with trigonometric identities, which I'll let you try for yourself as an exercise. And I've boxed this equation because it's extremely important. It's the tangent of beta goes as 2 cotangent, the tangent of theta goes as 2 cotangent beta of the quantity m1 squared sine squared beta minus 1 over m1 squared gamma plus cosine 2 beta plus 2. So in 514, why have I put this equation in this form? Because it indeed is a closed form equation for tangent of theta. The tangent of the turning angle is only a function of the incoming Mach number and the wave angle, that is the angle of the oblique shock beta, relative to the incoming flow condition. We call this equation the famous theta-beta Mach number equation or relation. It gives theta as a function of m1 and beta only. You can see it's rather difficult to solve for m1 or beta explicitly in a closed form analytical form. Typically, we use numerical methods, but in this classes, I'll show you one particular analytical solution for one of the other properties. Now, this is a very complicated equation that talks about how we change the turning angle to flow in incoming Mach number, and of course, the possible angles of the attached planar oblique shock. How does it behave, and can we learn anything about the physics from this particular equation? Let's explore it now. This is the graph of the theta-beta Mach number equation. It's called the famous theta-beta Mach number diagram or graphs. These are shown as 2 particular graphs for planar, that is two-dimensional, attached oblique shocks. On the x-axis, you have the deflection angle of the flow. That is the flow turning angle. On the y-axis, we have the shock wave angle. The shock wave angle is the angle of the wave front relative to the incoming flow. Remember, beta must always be bigger than theta for the solution to exist, and you see this on these curves. The Mach number is written as a series of families of solutions. For example, we can see each particular Mach number has one of these black curves. So M1 might be labeled as this particular line. And along this particular line, M1, the incoming Mach number, is always constant. Now you see for a given value of theta and a given value of Mach number, we have either 3 things happening. 1, we have 2 solutions. 2, we have 1 solution. Or 3, we have no solutions. So there's 3 particular cases that are possible for any particular value of Mach number, M1. So M in the theta-beta Mach number relation remembers M1. That's the Mach number of the incoming flow, not the normal or tangential components, of course. And this is only for gamma 1.4. We'd, of course, have to have a different graph for each particular Mach number. Why are these diagrams important? Of course, numerical methods weren't always handy, and it's easy to bring on a chart and simply for the correct gamma, look up a particular value of theta and Mach number and find the particular wave angle beta. From beta, theta, and M1, we could then find all the other properties across the oblique shock wave. We would do this for every oblique shock wave in the system as we march downstream. Now, I've labeled some particular contours and colored them as red and blue on this particular diagram. Families of shock waves for multi-value solution below the red line are indeed weak shocks. So everything below the red line are called weak shocks. This is the mathematical definition of weak shock versus strong shock, which I alluded to previously in the course, and this is where we mathematically define them. Everything above the red line are strong shocks. So the red line represents the division between strong shock and weak shocks. You'll notice that division happens where for any particular angle theta and particular Mach number, there's only one solution of the theta-beta Mach number equations. For example, right here, this is at about theta of 27 degrees, right here. And if I move my cursor up, you'll see it lands on this particular family of M, Mach numbers incoming the flow. Indeed, there's only one value of beta, which is about 64 degrees approximately from the graph, and there's only one solution. If I increase theta a little bit, there's no solution from this particular deflection angle. If I decrease Mach number a little bit, then of course, there's no solution. If I increase Mach number a little bit, there'll be two solutions. The second curve is the blue line. Everything above the blue line will have a Mach number after the shock, M2, of less than 1. You'll always have subsonic flow behind the shock wave above the blue line in the theta-beta Mach number curve. And this is shown mathematically, where, of course, M equals 1 as M2 equals 1 on the blue line. That's the division of the theta-beta Mach number curve, which doesn't happen, of course, on the singular solution like we just showed. Singular being one value solution. Everything below the blue line will have supersonic flow after the oblique shock wave. So you see oblique shock waves with a single turning angle could have flow that's supersonic or subsonic behind them, and they're called subsonic and strong and weak shock waves respectively. Of course, there's some weak shock waves which have supersonic flow behind them, but no strong shock wave has supersonic flow behind it, as you can see from the diagram. Take a few minutes and think about the properties of the theta-beta Mach number equation yourself so you can understand the possible physical solutions. Here's another graph of the breakdown of this particular wave, drawn in a different way. Once again, we have the theta-beta Mach number diagram. On the x-axis, we have the flow turning angle, which is shown in the diagram relative to the wave, and we have the wave angle, which is the y-axis, beta. We have an incoming Mach number M1. We're showing lines on the graph which are constant incoming Mach numbers from 2, 3, 5, and infinity. So the asymptotic limit of M1 going to infinity, we obtain, of course, a constant curve of M1 infinity on the theta-beta Mach number diagram. So for example, even if Mach numbers like 50 or 60, and we have a flow turning angle of, say, 50 or 60 degrees, it's impossible for a solution of the theta-beta Mach number to occur. And therefore, we cannot have an attached planar oblique shock, as you'll see momentarily. In the dashed lines, I've shown, once again, the division between strong and weak shock waves, which occur at the singular solution for the theta-beta Mach number curve. For example, we call this the theta max value. The theta max value at M1 equals 5 occurs at about 41 degrees, right here. See, there's only one solution for beta. You can go across and see that the wave angle in that case is about, say, 68 degrees for M1 equals 5. Now, you can see at lower Mach numbers, say 2, 3, 5, and infinity, the waves branch out and become larger and larger and larger, and of course approach some asymptotic value. What happens when we let M1 approach 1? This is another interesting question which I would like you to consider. What happens when M1 goes to infinity? Indeed, in these cases, you'll obtain deflection angles of 0. So as the Mach number goes to infinity, or Mach number goes to 0, we obtain particular solutions of beta and theta, which of course will correspond to the weak case and the strong case of normal shock. Let's think about some additional notes from the theta-beta Mach number diagram. Remember, the wave deflection angle varies with M1 only as a parameter. For any Mach number, incoming Mach number, there's a max deflection angle, which corresponds to the angle where there's a singular solution for beta. If the geometry, that is, theta, is greater than theta max, then no solution exists for the planar oblique shock wave, which you see in this problem. For example, for gamma 1.4, if we have theta of, say, 70 degrees, there's no solution on the chart for any Mach number. And we don't really know what happens in that case yet, but we'll discuss it momentarily. What happens indeed is a shock wave will be considered strong and it'll detach from the vehicle, as we see in the detached waves in front of reentry vehicles with high turning angles. We'll look at those pictures momentarily. For values of theta, the turning angle is less than theta max for a particular Mach number. There's always two valid solutions for the wave angle beta for each M1. There'll be a large value of beta and a smaller angle of beta. The smaller values of beta are weak solutions, which we showed, and the larger values of beta are strong shocks. Now, usually, weak shocks usually occur. Why is this? Well, it's totally determined, of course, by the startup conditions of the flow and, more importantly, the back pressure. In some situations, you'll have a strong shock appear, simply with a different wave angle, to match the back pressure of the flow. And we'll see these particular situations in some particular flows in this class. Remember, strong shocks always have Mach number less than 1. Indeed, normal shocks are always strong shocks. Strong shocks have subsonic flow behind them. Now, weak shocks, alternatively, may have subsonic flow behind them, but they usually have supersonic flow. So a weak shock, as you can see, might have supersonic flow behind it, and in the region between the two dashed lines resides subsonic flow, but that is bounded and weak shock solutions. So this little corridor between the two lines on theta, beta, and Mach number diagram corresponds to weak shocks with, of course, subsonic flow behind them. In this class, we looked at particular physical and computational simulations and experiments of oblique shock waves. And in particular, we looked at the planar oblique shock wave, that is the two-dimensional stationary solution. Remember, three-dimensional shock waves, all shock waves are really three-dimensional in practice, might not have planar surfaces. So the equations we developed are for planar shocks. Later in the class, we'll look at conic shocks, which are also shown in your class handouts. But unfortunately, no particular nice analytical solutions exist, and we find them numerically. We also discussed Mach angle, and we saw that the Mach angle indeed must be less than the wave angle, the shock wave in the flow. We then derived our equations by applying a control volume across oblique shock, and we were very careful to form equations that are nonlinear and algebraic in closed form, which we can solve with our previously developed approach for standing normal shocks through a substitution. We immediately showed the solution, and I encourage you to work through the values on yourself so that you can see their derivation. Indeed, we found that the thermodynamic properties, density, pressure, and temperature, the static values, all increase across a shock. But unlike standing normal shock waves, you might have a supersonic or subsonic Mach number after the oblique shock wave. And that, of course, depends on the theta-beta Mach number solution. If there's no solution of theta-beta Mach number diagram or equation for a given turning angle theta, it could very much be that instead you have a shock wave, which is standing off from the turning part of the vehicle, the point, and it becomes a shock wave, which of course is in front of the vehicle, a bow shock. We then looked at the summary and interpretation of the famous theta-beta Mach number diagram, and you'll see through problems in your class, you can practice using the theta-beta Mach number diagram to find solutions. Thank you very much for your time today. I'm Professor Steve Miller.